All right, we're with Anders Hejlsberg. How you doing, Anders?
I'm doing well, Charles.
Excellent. So we've been a while since we've seen you. What have you been up to? I mean, I know you've been busy working on the next version of C#.
Well, that seems to perpetually be true, and it still is. So yeah, we've been working on C# 5.0 and VB 11, I guess.
Wow.
Yep.
It's excellent.
Yep. And our big new feature there is asynchronous programming that we, have decided to delve into quite deeply. A lot of that actually based on input from customers and MVPs. It was a surprising outcome of one of our MVP summits probably a couple of years ago and a year and a half ago was that the one area that MVPs thought was the hardest to deal with was asynchronous programming. And I was kind of surprised by that. I go, really? And well, maybe there's something we could do there.
Yeah.
And so now we've done something.
Excellent. So let's be clear there. I mean, you've always had sort of the pattern where you begin invoke, end invoke, and then you had sort of this method async, blah blah blah, and delegates and whatnot. So what have you done to simplify that? I mean, what's going on here?
Right. So yeah, historically, yes, we've had the APM or the asynchronous programming model with the begin blah blah blah, end blah blah blah, and async result and whatever, and I think experience has shown that was very, very complicated for people to use. Heck, it's very, very complicated for us to use. So very few people can get it right. As sort of a remedy on that, we built the event-based asynchronous programming model, or the EAP, which the prototypical example there is Web Client, which I think a lot of people now use to do asynchronous downloading of stuff. And that one helps, but common to both of them is that asynchronous programming does this funny inside-out inversion of control to your logic. There's like the stuff that goes before the asynchronous call, which is just like normal code, and then there's the stuff that comes after that has to be put in a callback and sort of sits out of band, and you sort of have these two intermixed flows of control that are hard to tease out, and it gets particularly complicated if you want to deal with exceptions, because what if an exception occurs as part of the completion, and how do you propagate that out to someone who made an asynchronous call to you? So there isn't even this notion of an asynchronous call because your call has already returned. So how do you deal with that? And now that sort of gets you into, you have to have two events, like the normal completion or the exception completion, or you have to have two callbacks that you pass in, and it all gets real ugly real quick. And so we sort of wanted to try to allow you to think of your asynchronous programming more in the same way that you think of normal synchronous programming. Part of the inspiration here comes from F#'s asynchronous workflows, which some of you may be familiar with, which allow you to write asynchronous code, but you clearly see the flow of control of the asynchronous workflow. And even though the code doesn't execute synchronously right here with control going in here and control coming out the bottom and nothing else happens in between, like normal synchronous code, it still executes in sequence, but other things can get interleaved in between certain points of execution. And that's in the F# case, when you say lead bang or whatever, that basically says, evaluate this expression and assign it here, but in between you can cede control and let all sorts of other stuff happen.
Excellent.
Which is really what asynchronous programming is about, right? And so in a sense, we tease apart the mechanics of executing asynchronous code from the logical flow of control. And that served as, I think, quite an inspiration, and we started thinking more deeply about this, and sort of happened upon a model where we can allow asynchronous code to be written exactly like synchronous code, using the task and task of T classes that we implemented in version 4.0 of the framework. So in a sense, it's like some stuff that was already done in the task parallel framework, task and task of T. which represent, I think the, I think the computer science way of talking about task and task of T is futures or promises, or
Yes.
it's this notion that you get an object that represents a value to be delivered sometime in the future. And of course with generics you can strongly type it. You can have a future of T, which is something that will deliver a T in the future.
Nice.
Now task is actually exactly that. It's just we call them task instead of future. But if you think of them that way, so task of T is a thing that will deliver a T sometime in the future. So task of string is a future string. A string that is in the process of being computed but hasn't arrived yet, necessarily.
Yep.
Now on task of T, there's some interesting things you can do. You can, in particular, you can register a continuation. So you can walk up to a task of T and say, when you complete, please execute the following code. And that's roughly equivalent to the on download completed event on web client, where you're saying, hey, when you complete, here's the next piece of code I want you to run. And you can give it to it as a lambda expression, and then that gives you the value, the completed value, and now you can get to write your code. Now, you still have this inside out inversion, if you will, where your code has to be in a lambda, the code that executes upon completion.
Yep.
But you now have an object that represents this asynchronous computation or this task. And it can either represent, it represents it in the sense that you can take this object and say, I'd like to wait for you, or I'd like to ask what your status is currently. The object itself will encapsulate the return value or any exceptions that occurred, and you have one way of dealing with it.
Excellent.
And what we've done now in C# 5.0 and VB11, or what we're doing, and what we have a CTP out, or a tech preview out of, is language support for tasks. And it really sort of amounts to just two things. A new modifier called async, which you can put on your methods, and that designates the methods as asynchronous.
Okay.
And then there's a new operator called await. And you can apply that to a task, and it asynchronously awaits the task, and then delivers the result. So if you await some task of string, then the result of awaiting it is a string.
Yeah.
Now, when we talk about awaiting, though, there are sort of two ways you can think of this await operator. You can think of it as mechanically, what does it do? And then you can think about logically, what does it do? Now, logically, it waits for a task to complete, and when it's complete, then it continues the logical flow of control. But we're talking about an asynchronous flow of control here. And on every await operator, actually what happens mechanically is that the method returns control to its caller. And then it registers the rest of the method as a continuation on the task that you're waiting on. Which is a little bit mind-blowing at first, but this is sort of the deep difference between the mechanics of how you execute the code and the logical flow of control. From a logical standpoint, an asynchronous method might take, hours to execute, and there are big, long pauses in between where you're waiting for asynchronous operations to complete. But that doesn't necessarily mean that there isn't a for loop in there. There might be a for loop where you're downloading and playing movies, and it takes like an hour for each of them to play before you start the next one. But logically, why should your logic look different just because the code takes a long time to execute? Do you know what I mean?
Yes.
And so you can think of the logical flow of control, and then there's the mechanical way that it actually executes, right? And I think the beauty of what we've done here is allowing you to think of asynchronous code just like you think of synchronous code. You can think of the logical flow of control.
Excellent.
Yet you can play by asynchronous rules where, when you await a task, lots of stuff can execute until the awaited task comes back, but you have not lost your sort of logical place in the world.
Excellent. And you don't have to deal with a bunch of callback management and all this stuff as you mentioned earlier.
Well, the callbacks in a sense are still there, but you don't see them. And this is one of the, if you've ever written some of this callback code, other than just the simplest, I'm going to download the string, and when it comes, then I'm just going to store it somewhere, and that's that, or process.
Yeah.
If you tried to do something a little more complicated, let's say, I'm going to go to some website, scrape a bunch of URLs, then I'm going to concurrently download all of those, and when they're all there, then I'm going to mash them up and save them in a file or whatever, like something more complicated than that, right?
Yes.
Or the first three, once I have those, then based on those, I'm going to go do other downloads. And if you ever tried writing that with our current support, even with our best current support for asynchrony, you'll find that it is very complicated, and you end up implementing these horrendous state machines, you know, that like, well, if the first download has completed, but the other two, so you have to have a counter of how many you've got going, and then that's got to count up to the max number, and then you can continue with the next piece of work, and so forth. And we're terrible at doing stuff like that as humans, you know.
Sure.
Compilers, on the other hand, are great at doing stuff like that. They can take a piece of code that you write, you know, with a bunch of await operators in it, and they can turn it into a state machine. And in fact, it is very, very similar to what we do with iterators already. If you've ever looked at how iterators get implemented, you know, they allow you are allowed to think of a logical flow of control where you yield out values, right? And the compiler turns that into this complicated state machine, you know, where it has to lift locals into fields of objects and whatever, but the beauty is you don't have to think about it because you understand the mechanical mapping that's happening, and once you understand that it does that, then fine. Now you can think about the logical flow of control. That's what we're good at thinking about.
Yes.
Now asynchronous methods are actually remarkably similar. It's a different mechanism underneath. It's not IEnumerables, it's tasks. And you don't yield values at every point. You yield control and wait for a task to complete, and then you continue executing until the next task that you wait for. And so control sort of comes in and out of your method. It does so by continuations, not by move next calls, you know, but in principle it's the same thing, right? That you take all of your local variables and you lift them into an object that the compiler generates, but you can still just think of the logical flow of control. And that's, I think, what's really interesting about this feature. Now there are a bunch of deeper aspects to it too, how it helps, you know, it definitely helps make your UI more responsive, you know, and if you saw my presentation, you'll see how that's clearly, you know, a wonderful thing, and it can make, you know, writing these responsive apps much easier. But interestingly, it also helps in server scalability. Because if you think about how a web server runs internally, like ASP.NET, if you're writing, say, a service, an aggregator service, or for that matter, you're writing some web service, or even just some web page that needs to call some web services, say 2 or 3 of them. Well, first of all, you really would like those calls to happen in parallel,
yes,
or concurrently with each other, right? So you don't want to first synchronously call one, wait for that to complete the next. It's just going to take a long time for you to service that request. So that's one place where asynchrony can help you, because asynchrony allows you to issue all the requests, boom, 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 and then await them all together. And then when they're all there, then you can continue. ASP.NET has, for that reason, an asynchronous programming model today, but it is not simple either. They made a more modern version of it that allows you to use web client, but again you get into these inversion of control or flow, you know, scenarios where with asynchronous methods it becomes almost trivial to write asynchronous code in your web servers. And it's interesting too to think of, because, you know, one of the things that is hard about web servers today, and about finding the sort of ideal number of requests to service or to let in at a time, and the ideal number of threads in the thread pool, is that a lot of code gets written synchronously, simply because that's sort of the path that we're led down by libraries and just common practices, right? But when you write, and as long as your synchronous code doesn't do a lot of blocking, you're fine, because you're keeping the CPU busy. And when the CPU is busy, fine. It's like if it's busy with this request or the other request, I mean, it's busy, right? It couldn't possibly do any better. It could split its work differently, but yeah. In the aggregate, it would take the same amount of time, right? But with asynchrony, that's not true, or with blocking APIs, that's not true. If you make a blocking call to some network service, or say you call some web service that takes half a second to respond to you, you're blocking a thread now for half a second. Now that, of course, the hardware is smart enough to not have one of the CPUs, if it's a multi-core CPU, it's not going to have one of the CPUs sit there for a half a second and do nothing. It's going to notice, this thread is blocked, I'm going to leave it alone until it unblocks. And I'm going to service other threads. But the problem you run into now is that you may not have enough threads to service. So now you're going to let in some more threads, because this guy over here is blocked. So let's spin up some more threads so we can keep the CPUs busy, right? And then you spin up more and more and more threads. Now let's say your workload changes, where you don't have a lot of blocking all of a sudden. Well, now all of a sudden you got all these threads that want to be serviced. And now you start starving, now they start starving each other, right? Because the CPUs have to jump around and service all these, and so you have all these context switches, you know. And so it turns out that it's very hard to determine the ideal number of threads to have running when you have lots of blocking going on. If there's no blocking, the equation is trivial. You want to have exactly as many threads as you have CPUs, because what's the point of having more? You're just making requests go slower then, right?
Yep.
So in a 4 CPU machine, you would want to have 4 threads. But if your threads block for, say, 50% of the time, well, then you need 8. Or if they block for 80% of the time, then you need a heck of a lot more threads. But then if your workload changes, or if little requests come in that aren't going to block, they could get hung up behind one of these long blocking threads. Do you know what I mean? And so it becomes really hard to correctly throttle, and you might, you know, you might never reach that elusive 100% CPU utilization, you know, because you can't find the correct throttling point. With asynchrony, it gets a lot simpler, because you're not spending CPU resources on things that are not CPU related. If it's I/O related, fine. You're only gonna occupy the CPU for the amount of time it starts to get the request. It takes to get the request started and to service it at the end. And in the interim, you can service other things on that thread.
Absolutely. I mean, in some sense, we've had a lot of conversations about, you know, threads in reality. When we talked about concurrency and parallelism, and why not make it easier. And tasks sort of abstract threads as well. You think of task-based parallelism, you're not really thinking in terms of threads, you're thinking in terms of tasks. So now you have task-based asynchrony, which is also cool. But in the end of the day, as you mentioned, it does all come down to threads at some level. Can we talk a little bit about that?
Well, it does and it doesn't. I mean, there are certain things that okay, so we sort of have to talk about the different kinds of asynchrony that you might have in a system. We've talked here about I/O asynchrony, network asynchrony.
Yep.
There's also computational asynchrony, if you will, but you can think of them all under a broad umbrella. Let me take my example of the UI thread. Let's say you have a system that you know, for one reason or another, needs to run things on one thread. It could be the UI thread, or it could be you're servicing an ASP.NET request, and ideally you don't want concurrency, and that's you know, from the point of view of that request. You don't want multiple threads banging on the same data structures for a single HTTP request. We tend to always have just one, you know, so you can think of logically as you're servicing requests on a single thread, or you have your UI running on a single thread. Now, let's say you need to do some I/O. Well, it makes perfect, or some network requests, right?
Sure.
It makes perfect sense to just spin them up and then have the hardware the I/O DMA buffers or what have you, your network card, deal with the traffic, and then wake you up again when it's ready with the response. There's nothing for the CPU to do once you've gotten the request going. All of the record of that request can sit in-memory data structures in the kernel, and the driver can know to wake you back up when the result is there, right?
Yep.
That's network asynchrony. You know, you have sort of a beginning and an end to a request, and in the middle you can have the CPU do other things. Now, computational asynchrony is you know, sort of similar in that, let's say you have to do a very big, expensive background operation, but you want the UI to remain responsive, right? So you want to keep the UI thread. You want to just have little pieces of work go on the UI thread. And so you want to make your background computation into a task. And then you want to say to that task, go run this on some other CPU, you know, or time slice with this one. But then you want to await the result of that thing, which means you want to say, once it's done, then I want to continue here on the UI thread with the result. And it's really just like making a network request, right? It's like, send a request, and once it's done, and you have the result, now I want to continue with the result and update the UI. So you can think of the two under a unifying umbrella here called task. And task can represent all of these equally well. It can represent a piece of work that's running somehow, somewhere, that will compute a value in the future, right? Now, whether that value gets computed by bits flowing over the internet or electrons getting shuffled around in one of your multi-core CPUs here, it doesn't really matter, you know. Common to the two are, you know, there's like stuff that kicks it off, and then there's the orchestration of having maybe 4 of them going, and then when they're all delivering their results, then you want to do something else based on that, asynchronously, right? And the language extensions that we made are the language extensions that allow you to write these logical flows of control that orchestrate asynchronous operations. And the asynchronous operations can be I/O, network, or computationally bound. Now, we started with the task parallel library with an emphasis on the computationally bound. And now you could sort of say we're growing it into I/O and network bound as well, and then we're putting a language umbrella on top of all of it that allows you to build asynchronous applications. So I hope this makes it a little more clear.
Totally.
It is a very confusing area to think about, because there are so many sides to this question of concurrency and threading and multi-core and whatever, and we're all looking for one answer to everything. And there isn't one answer to everything,
sure.
But there are some unifying things that you can do, and that's why I'm excited about this work, because it allows you to focus on logical control flows of asynchronous code, you know, irregardless of where the asynchrony is coming from.
True. So, I mean, and of course, people are already, they're watching your talk now or have watched it. So I want to kind of back up a little bit and talk, because, I mean, since you're Anders, man, this is C# is your language, you're a language guy. And I kind of wanted to get a sense of kind of a little historical perspective on when these ideas started to evolve.
Yeah.
Clearly, you knew about tasks since they were invented, and you know about futures, blah, blah, blah. But the interaction between the language and the library is very, very interesting in this case. Yeah. And so I just wanted to get kind of a sense from you.
Now, you said that I'm you know, the C# guy, and actually I'm also, you know, the sort of the fellow that takes care of all of our managed programming languages.
Correct.
So
Correct.
You know, and it's important to note that everything we're talking about here applies equally well to BB.
Excellent. Excellent.
Now, yeah, it's interesting with language support. I've always sort of been a believer in trying to identify you know, idioms that people use, and then seeing if we can make their work easier by having the language do the dirty work, you know, and there was a bunch of stuff, you know, I mean, there's a bunch of similarities between this work and, say, LINQ, for example. LINQ was a lot about, you know, at the high level, it was about allowing you to express queries and do more declarative kind of programming. But if you look at mechanically what it was about taking all these like for loops and if statements and convoluted, logic that you write with dictionaries and lists and arrays and turning it into a higher level paradigm, and having the compiler do some of the heavy lifting where, if you want to evaluate a predicate over a collection, instead of you having to write a method and make delegates to the method, you just write a lambda expression and it's all nice and easy, right?
Yep.
And in a sense, the similarity here is like asynchrony has been, it's important and people do it because it makes a difference in their apps, but the mechanics of doing it are horrible, and it's something that a compiler could do a lot better with the right paradigm in place, right? And so there's always this symbiosis between, I think, the frameworks and the languages that you can make. The sum is greater than the pieces that went into it, right? If you do it right, and I think with this, just like with LINQ, there's a framework side to it, which is the task parallel library, and in particular the task abstraction, which really is a future. And then there's the language stuff that we did on top of that, right? And now we can sort of take those two together, form this wonderful new whole called, an asynchronous programming model with language support, right?
Excellent.
Now, as I said earlier, this work has been very inspired by work that Don Syme has done in F# with asynchronous workflows, and also I would point at folks like Jeff Richter, who actually built a whole library to allow you to do asynchronous programming using iterators, because he was smart enough to realize that, hey, the kind of transformation that the compiler does here with taking my locals and making them fields and objects would allow me to have my locals sort of across points where I yield control, just like in an iterator, and so I could actually sort of torque my iterators around and program asynchronous flows of control that way. And it works, and there are a bunch of people in the industry using it, but of course it's never as good as if you add real language support. And then I think the difference here too is that we're basing our implementation not on IEnumerable, which doesn't really fit the bill, but on task and task of T, but with the same kind of compiler transformations.
Excellent.
So there's a lot of it's funny sort of digging in the archaeology of it. This is an area where a lot of stuff's been going on for a while.
Yes.
Yeah.
This is true.
Yeah.
And you talked about the async keyword a couple of years ago at PDC, right? Or a year ago. You did a nice talk on the future of C#.
I didn't talk last year. I think Luca, it might have been Luca. Who talked about it. Yep.
So I want to, since you mentioned, VB, right? I mean, the VB doesn't necessarily have the facilities to implement what you did for C#. In some sense, you had to add some new things to the language.
So,
what were those?
Well, so VB did not until the work that we are doing in VB11 did not have iterators, and so they did not have the mechanics in place inside the compiler to do the lifting and the generating of objects that are in a sense your heap-based stack frames, if you will. But they've done that work, and they've done it for both iterators and asynchronous methods sort of in one go, because it's really the same work. In fact, this project to build the asynchronous programming support has been a joint project between C# and VB, very much in the new spirit of co-evolution, that we started in the previous release. So it's been joint program management, joint development, a single team implementing it in both compilers. It's been great.
Excellent.
Yeah.
And so the final question I would ask you is, nothing is for free, right? So when you simplify, when you abstract complexity away for those of us that want to compose and not have to think about the plumbing, which is what .NET is all about, right? When you were involved in the creation of it, that was your vision. But with that always comes some amount of expense. And so I wanted to ask you, what are some of the costs of simplifying asynchronous programming that you can think of in terms of, I can't think necessarily what they are. This is why I'm asking you. But
Well-
you know, that's what I wanted to ask. It's a weird question, but I think there's
Yeah.
some sense to it.
I think when you evolve a language or two languages, or every language over its lifetime accrues more features, and therefore it gets more complicated, and this adds a little bit to that, right? And ultimately, we're all going to cave in under our own weight, but it might take a good long time. I mean, heck, COBOL and Fortran are still out there, right? After what, 40, 50 years, or So I don't foresee us caving in anytime soon. I do think we try to be very judicious about adding as little syntactic surface area as we can for every new feature, and adding as little conceptual baggage as we can. And I think this feature, it amounts to a single new modifier and a single new operator, and it brings tremendous simplification in an area that is of growing importance and relevant to any kind of modern app that you write. And at that point, you kind of go, yeah, it's worth it. It's worth it. And then that's really sort of the way we got to look at it.
Cool.
Yeah.
Well, hey, it's always great to come and talk to you, Anders. People who are watching this, Anders is going to be on Channel 9 Live, I believe, probably before you have a chance to watch this. But
yeah, I'm looking forward to that.
That's going to be fun.
Yeah.
Anders Unplugged for an hour. That'll be great.
As long
And
as it
hey,
takes, yeah.
great job. It's great to see that you
Thanks.
guys are pushing forward
Thank you. That's
in
fun.
this age of cloud computing and asynchronous computation everywhere.
That's awesome.
Right?
All right.
Take care.
You too.